Welcome back to the micro engineering course, and from today's lecture onwards we will be starting with our second module, that is waveguide and passive microwave waveguide junction based devices. So I welcome back again and good morning to all. So let us start with the second module from today's lecture. So in this particular module, as I already explained to you in the syllabus content, the waveguides are the second chapter, and we are going to also see some of the passive waveguide junction based devices and their formulation of a scattering matrix, and thereafterwards we will see non-reciprocal devices and devices which are made by using special materials like ferrite, and then we are going to see the numerical examples which are simply based on the calculation of the properties of the waveguides. So first again, in order to understand the field mechanism or the electric and field analysis that we are going to make in the analysis of the waveguide. So waveguides, first of all, we need to form a foundation knowledge about understanding the field behavior which is getting passing through the given waveguide. Okay, so the electromagnetic signal, the micro signal, waveguides are used as a transmission lines, and waveguides also acts as a conductor in order to carry the microwave power at a high frequency, and also they are capable to carry the microwave signal at a high power also. So waveguides are as good as that of the transmission line, but here the waveguides are made hollow, and in this particular module we are going to derive the field expression for the electric and magnetic field through which the complete microwave signal propagation is described into the waveguide. So let us start with a discussion of a waveguide theory. And first of all, please again remember that we are going to take the help of a field theory. So some of the initial lectures will consist of deriving the derivation related to the field analysis. Okay, so these derivations will be made as simple as possible in order to understand you. Okay, and later on I will tell you a shortcut technique in order to remember and recall these derivation in an efficient way for both, that is rectangular and circular waveguides. Okay, so as on when we come across that particular part of rectangular and circular waveguide, these generalized expression forms of analysis we will convert into particular waveguide form. Okay, so I will tell you how to remember these derivation in a short and quick way, but before that you should understand how these field generalized equations are developed. So today's lecture we will devote to produce generalized field expression, so that these field expression we can use in a particular waveguide, and then applying a proper boundary condition we will develop a particular field equation for a given particular waveguide. Okay, so let us start with first discussion of general theory of a waveguide analysis. Okay, so I will open the notes. Now first of all I need to orient this. Right, now let us start with the discussion of general theory of waveguide analysis. So I will choose this blue color now. Okay, so in this particular topic we are going to discuss general theory of waveguide analysis. Okay, so this part is very important in order to understand how to derive the field equation in a general format. Okay, so here the topic is general theory of waveguide analysis. Okay, so first of all we will see what is this general theory of waveguide analysis and what exactly we are going to analyze. Okay, so for that I will draw a simple diagram over here, and I will explain you the field which is going to get propagated through a particular waveguide. So in our syllabus we are going to focus mainly on two different types of waveguides, that is rectangular waveguide and circular waveguide. Okay, so I will draw a diagram. Okay, so let's say this is a rectangular cross section. Okay, and this rectangular cross section so in this way, right? So this is a cross section of how the rectangular waveguide look like. Okay, it has all four walls. Okay, so here you can indicate this is the first wall, this is the second wall, and the third wall, and fourth wall. Okay, so the four wall contain metallic box can be treated as a rectangular waveguide. So this is the example of how the cross section of a rectangular waveguide look like. Rectangular waveguide. So we will first describe briefly what do we mean by a waveguide. So waveguides over here, they are best described as transmission lines. Okay, the transmission lines which are made by hollow metallic pipes. Used for transmission of microwaves. Okay, so how we describe what do we mean by waveguide? A waveguide is nothing but a transmission line which is made by making use of hollow metallic pipe structures and which is used for the transmission of microwaves. Okay, so one may ask me the question, then if we have the coaxial cable and other type of a transmission lines, why the waveguides are used for the transmission of microwaves? So the reason over here is the microwave will offer certain advantages to us. Okay, so the first advantage of using a waveguide over a transmission line or a cable or a wire is microwaves can be carried at a high power. Microwaves can be transmitted at high power. So the only choice when we want to transmit a microwave signal which is at a very high frequency and at a very high power, then it can be used for the transmission. So the microwaves can be transmitted at a high power, right? So for carrying the micro signal at a high power, we normally make use of a waveguides because waveguides are rigid in structure as compared to transmission cables. Okay, so they can handle the losses and the heat dissipation, and that's why transmission of a microwave signal at a high power is going to make use of the waveguides rather than a transmission line or a cable. Okay, so in simple word, how we define a waveguide then? A waveguide is nothing but a transmission line which is constructed by using hollow metallic pipes. Okay, and it is used for the transmission of microwave signal. Now please remember here the waveguide is made hollow. Okay, so why it is made hollow? Please remember over here the inside of this waveguide, please remember, is made as a hollow, right? So the inside of this, okay, so the internal waveguide is made as a hollow. Now it is made hollow because we know that when the microwave signal gets propagated, it will propagate on the surface of the conductor. Okay, so being operated at a very high frequency, the signal will not penetrate deeply. So rather the signal will travel on the surface. So there is absolutely no need to fabricate a waveguide with a solid material. Okay, so instead of that, the inside material here you can fill with a dielectric. Okay, so when we keep the internal part of the waveguide as a hollow, so definitely the air will be filled automatically, and the air will act as a dielectric. Now please remember, instead of filling or keeping the waveguide empty, that means by filling it with the air, you can fill the inside part of the waveguide with some other dielectric material also. Okay, so we'll come to that particular point later on. So for time being, you just understand that waveguide is a transmission line, and it is used to carry the microwave signal from one end to another end at a high frequency, and they are constructed by using a metallic pipe which are hollow in nature, right? So next is, let us discuss the mechanism of wave propagation. So for that, what I will do is I will draw a vector diagram over here in this way with a 3 axis. Now this explanation, whatever I am giving, so this explanation is related to our derivation, that is the next part that we are going to see. Okay, so let us say here there are 3 axes in a 3-dimensional space, x, y and z. Okay, so let us say there is a electric field existing along the x-axis. Okay, so along the x-axis there is a electric field, right? And along the y-axis, let us say there is a magnetic field. Okay, so the magnetic field is indicated by H. Okay, so the electric field vector is available across x-axis, right? Magnetic field vector is available across y-axis. Okay, and these two fields are oriented, so that is the electric field and magnetic field, they are oriented perpendicular to each other, and that's why this gives transverse electromagnetic wave. Okay, so please remember what is the meaning of transverse. So please remember, here we use that particular term called as a transverse. So transverse, the meaning of the transverse is perpendicular. Okay, so here electric field exists along x-axis, right? And magnetic field, which is represented as a vector, it is existing along the y-axis, right? X-axis is perpendicular to y-axis, therefore electric field and magnetic field are said to be transverse to each other. They are said to be transverse to each other. Okay, so what do we mean by transverse? Transverse means they are perpendicular to each other. So here we assume that the electric field is located along x-axis, magnetic field is located along y-axis, right? So along x-axis the electric field is going to vary, and similarly along the y-axis the magnetic field is going to vary. Okay, and along the z-axis there is a propagation of this particular wave. Okay, so the variation of electric field we will find along x-axis. So along x-axis electric field varies, right? And along y-axis there is a variation of magnetic field. And as these two fields are perpendicular to each other, when they combine with each other, they start propagating along the z-axis, because we know that when the two vectors are perpendicular to each other, their cross product is going to generate a third vector, right? And this third vector is along axis z-axis, right? So this z-axis we normally call it as a axis of the propagation of the wave. Now what is that wave? Now that wave is made up of electric field as well as magnetic field. Okay, and how these two fields are oriented? As the two fields are oriented perpendicular to each other, we call these fields as transverse fields, right? These fields are known as a transverse fields. Okay, so we know that along x-axis there is a electric field, right? And along y-axis there is a magnetic field, So the field which exists along x-axis and y-axis, these are transverse fields. And the two both fields, that is electric field and magnetic field, they will propagate along the z direction, giving rise to the third vector. Okay, so the z direction we call it as a longitudinal field. So whatever field that exists along the direction of propagation, now here the direction of propagation is a z. Okay, so the field which exists along the direction of propagation, we call it as a longitudinal field. So here I will write propagation field, right? This propagation field we normally call it as a longitudinal field. Please don't get confused between these particular terms. These are very commonly used terms in the electromagnetic field analysis. So please remember, longitudinal field is the field which exists along the direction of propagation. Okay, and the transverse fields are those fields which are oriented perpendicular to each other, and as well as they are perpendicular to the direction of propagation also. Okay, so I hope you understood this particular terminology. Now here, what is the objective of general theory of a waveguide analysis? Okay, so the objective of this particular analysis that we are going to see very soon, the objective of this derivation is to express these transverse fields. Okay, so the transverse fields mean the fields which are located along the direction perpendicular to the direction of propagation. Okay, so here I will write the objective. I will choose a different color so that you will come to know what is the objective of deriving this derivation. So our objective, okay, so to express transverse fields, that means the fields which are located along x-axis and y-axis, right, in terms of, okay, in terms of longitudinal field, okay, and find expression for all the field components. Okay, all the field components in three-dimensional space. Okay, so I will elaborate you what is the objective of this derivation. Say the objective of this derivation is to develop equation for the transverse field components which are expressed in terms of longitudinal field component, which all will give us the total field components in the three-dimensional space. Okay, so the broad objective of general theory of a waveguide analysis is to design or formulate the equations of the fields which are existing in the transverse direction in terms of longitudinal field components, and find out all the possible field components possible in a given three-dimensional space. Now here we have taken a three-axis system which represent a three-dimensional space. So here we have x-axis, y-axis and z-axis. Okay, so these are the axis which represents our coordinate system in a three-dimensional space. Now here the electric field we have, and we have the magnetic field. So when the electric field and magnetic field are expressed along these axes, so there will be three different sets of these fields. Okay, so the electric field which exists along x-axis is given by Ex. The electric field can also exist along y direction, which is given as a Ey, and similarly the electric field can also exist along the z direction. So here we get three values or three sets of electric field. Okay, so the electric field can exist along x-axis, it can exist along y-axis, and it can exist along z-axis. The same is true for the magnetic field also. So the magnetic field is also available along x-axis, we write as hx. The magnetic field is also available along y-axis, we write as hy. And similarly, the magnetic field may also be present with the z-axis, which we write as a hz. So here we also got three set of magnetic field vector. Okay, so here the field components, so what ex, ey, ez and what is hx, hy, hz, what we call it as a field components. So please remember the electric field components, we can write it as a electric field component. Okay, so electric field components are ex, ey and ez. Okay, but out of which ex and ey we call them as a transverse. So ex and ey we call them as a transverse components because the ex and ey electric fields are perpendicular along their direction along x and y axis. So ex and ey components are called as a transverse component. And the component of the electric field which is located along the z direction, we call it as a longitudinal component. So this we call it as a longitudinal component. See, longitudinal component means the component of the field which is located along the direction of propagation. Now in this particular diagram we have considered the direction of propagation is along z, right? So similarly we can express how the magnetic field components are given then. So the magnetic field components are, I will write over here. So how the magnetic field components are given on the similar basis, the same technique we use over here. So how the magnetic field components are given, these are given as a hx, hy and hz. Again the same hx and hy we call it as a transverse component. Okay, and the z component of the magnetic field we used to call it as a longitudinal component. We call it as a longitudinal component, right? So our objective, say I am illustrating what is our objective. Now here what we want is, we want to develop equation for ex, ey and hx, hy in terms of, or I would write this as a function of ez and hz. Okay, so what is our aim over here in this derivation? We want to develop equation for transverse field component which are ex, ey, hx and hy, which are written in terms of longitudinal field components, that is ez and hz. So here I hope you understood what is the objective of today's derivation. In today's derivation, what we are going to do is, we want to develop expression for ex, ey, hx and hy. All these are called as a transverse component, please remember. Okay, in terms of longitudinal field components, the longitudinal field components are ez and hz, right? So I hope you understood what is the today's objective. So there are in total, so ex, ey, hx and hy, these are 4 transverse component. Transverse field components. Okay, and there are 2 components, ez and hz. These are 2 longitudinal component. These are 2 longitudinal component. So in total, how many components we get? So in total, we get 6 components. Okay, so here what we want is to develop the component equations for transverse field components in terms of longitudinal field component, and today's the objective of the derivation is same. Okay, so let us we are not going to discuss these equations specifically with a rectangular waveguide. Just for the illustration purpose, I shown you what is a waveguide by drawing a rectangular waveguide. The waveguide can take shape of any way. For demonstration purpose, I took the rectangular waveguide. Okay, so let us go ahead and derive the derivation for transverse field component in terms of longitudinal field component. Okay, so here let us begin the derivation. Okay, so I will start the derivation here. Now I hope if you want, you can take your pen and paper, and along with me you can also jot it down and this will increase your practice of deriving the thing. And once you derive the thing along with me, you will also come to know the main feature of this particular derivation, and you can recall this particular derivation in a better way if you derive it by your own, right? So let us say the electric field. So the electric field, or we say a total electric field, it is given in terms of electric field in transverse direction, right, plus electric field in longitudinal direction, right? And similarly we can write total magnetic field. Total magnetic field is given as a total H. It is again same, magnetic field in the transverse direction, okay, same, and magnetic field in longitudinal direction. Okay, so first of all we need to write in general equation for total electric field and total magnetic field. Okay, so the electric field equation I will write like this: electric field E is equal to ET, where the suffix T stands for transverse component. Okay, and the longitudinal component I will write as EZ Z cap. Let us call this an equation number 1. Now I understood that what is the ET? ET is a transverse component and EZ Z cap is a longitudinal component. So when we add these two, we will get a total electric field, right? Similarly, the H, magnetic field component, how it is written? The magnetic field component along the transverse direction, HT, plus the magnetic field component along the Z direction. Okay, let us call this an equation number 2. Say the first component over here is a transverse component. You can write in this way. And the second component is the longitudinal component, right? So this is in general the total electric field and total magnetic field is given, right? So here what we do is, now we make use of a differential operator. Okay, so the differential operator del, okay, so from the field theory and in electromagnetics, okay, so the del operator you already know. So the del operator, how it is given in three-dimensional space? In three-dimensional space it can be expressed as a along 3 axes, dabba by dabba x of x cap. You can write in this way: dabba by dabba y of y cap, right, and dabba by dabba z of z cap. Okay, but out of which the first two component over here, they are transverse component. Okay, and the last component along the z is a longitudinal component. So we know how to write the del operator in electromagnetics. Okay, so how we can write the del operator? Let us call this part of transverse component as a del of t. Okay, so how the del operator is given then? Del is equal to del of t, which represent this part, transverse component, right, plus I will write dabba by dabba z of z cap as it is. Okay, so let us call this an equation number 3, and this equation 3 is taken from equation 4, right? So we recall a Maxwell equation. Okay, so what is a Maxwell equation for Faraday's law? So Maxwell equation for Faraday's law, I will write here Faraday's laws of electromagnetic induction. So how it is written? We know that the Maxwell's equation for Faraday's law is given as del cross E, right, is equal to minus j omega mu h, right. Let us call this an equation number 5. Okay, so this is a Maxwell's equation for Faraday's law. Okay, so what we do is we substitute equation 1 and 2. Okay, so equation 1 and 2 in equation number 3. Okay, and then we put this into equation 5. So what is del? This del we take from equation 3, this E we take from equation 1, and this H we take from equation 2. So what will happen when we substitute equation 1, equation 2 and equation 3 all together in equation 5? Okay, so when we substitute del is substituted from equation number 3. So in equation 5, so here I will write substituting del from equation 3, right, E from equation 1, right, and H from which equation we need to substitute the value of H, magnetic field, total magnetic field, that is from equation 2. Okay, into equation 5. So when you substitute equation 1, 2 and 3 all together into equation number 5, what we will get? The expression I will write here. When I substitute the del operator, what I will get is del of t plus dabba by dabba z of z cap, right, multiplied by del cross E. Now this E is from equation 1, Et plus Ez z cap, right, is equal to minus j omega mu, and you substitute this H from equation 2. So I will get H of t plus Hz z cap. Okay, now you simplify this particular equation and take the multiplication on the left hand side. What we get? So when we simplify and take the multiplication, del of t cross E of t, right, plus del of t into Ez z cap, right, plus dabba by dabba z of z cap cross Et, right, plus dabba by dabba z of z cap, then with this term Ez z cap, right. So this I took all the multiplication of the bracket term on the left hand side, and similarly here the right hand side I will write j omega mu into bracket H of t transverse component and Hz z cap. Let us call this an equation number 6, right. So we observe this equation number 6 very carefully. Okay, so this equation number 6 we will study first. Okay, so here first is any cross product with z cap. Okay, so when you take any cross product with z cap, it is going to get located in the xy plane. Okay, so here we note. Now for noting I will, so important thing to note. So what is a note? The first thing that we need to study, that any cross product with z cap. Okay, so z is a longitudinal direction. When we take the cross product with the longitudinal z component, it will be located, in xy plane. Okay, so when you take the cross product with z cap, it will get located in the xy plane. Okay, second observation, cross product of any two vectors, cross product of any two vectors in xy plane will give longitudinal vector, right? So if we take cross product of any two vectors which are supposed to be located in x and y direction, then it will give rise to the third vector which will get always located in the z plane, that is along the longitudinal direction. Okay, and third important observation, we can see that the cross product of a vector along itself, cross product of vector, so let us say vector z cap along with itself, z cross multiplied by z cross is always 0. Okay, so what we do is in equation number 6 we will apply these observation. Okay, and here the first parameter over here, now see the first parameter. So the first parameter is del of t cross E of t. Now these two field components are indicating that they are in a transverse plane. So T stands for transverse plane. So when you multiply two vectors, when you take the cross product of two vectors which are in xy plane, they will provide you a longitudinal vector. So this product will produce longitudinal vector, please remember. In z direction, please remember, right? Because these original two vectors are in the xy plane. So when you take the cross product, it will generate a third vector which will get located in the z direction. Okay, and the next term, that is the last term over here, this one. Okay, so what you can guess about this particular term? So here dabba by dabba z of z cap into EZZ cross product, right? So this particular cross product over here, I forgot to write over here the cross product, but please remember there is a cross over here, right? So EZ Z cap. So the cross product, we apply the third observation. We know that the cross product of the vector with itself is 0. So that's why the fourth term in equation number 6 is going to become 0 directly. Okay, so we make use of these observation in equation 6 and we will rewrite the equation. So the first term is as it is. So the first term, what it will give? It will give del of t multiplied by E of t, right? So the second term, what is del of t multiplied by EZZ cap, remains same, and the third term will also remain same, dabba by dabba z of z cap cross E of t. The fourth term will become 0. And here on the right hand side on the equation number 6, we will take individual multiplication with the outer term minus j omega u, j omega mu, okay, h of t, we take separate multiplication minus j omega mu hz of z cap. Now let us call this an equation number 7. Okay, so what we do next is we will equate transverse field component on the both side of equation 6. So here equating transverse field components on both sides. Okay, so first of all you should know what are the transverse field component. So on the right hand side of equation 7, the transverse field component is indicated by this particular term, right? And similarly on the left hand side you need to equate the transverse field component. So what it will give? So the equation that I will get is del of t multiplied by, say, please remember here I will underline that term. This term is not going to give you the transverse field component, but it will give longitudinal field component. So the only transverse field components are this one, right, and this one. Okay, so I will write those on the left hand side. I will get those bracketed terms. So into, I will change the color. So this is del of t cross EZ component, right, plus deba by deba z of z cap into E of t. And on the right hand side, if we equate only the transverse component, that is underlined over here, minus j omega mu h of t. Okay, so what we did, equation 7, we have equated on the left hand side and right hand side the transverse field component, right? So we will write this particular equation in terms of magnetic term. Okay, so what I will do is I will write h of t is equal to, how that can be written then, minus 1 upon j omega mu, right, into bracket del of t cross Ez z cap plus deba by deba z of z cap multiplied by E of t. Okay, so what I did is I wrote the above equation in terms of h of t, and let us call this an equation number 8. Okay, so if we follow the same technique over here, and if we make use of the Maxwell's law for the ampere, okay, so similarly we use Maxwell's law for ampere. So what is that Maxwell's law for ampere? Del cross H is equal to, we know that it is the deba d by deba t. Okay, so if we use this particular Maxwell's equation, and when we perform the similar operation over here, see here we started with Maxwell's equation for Faraday law in equation 5, and we came that h of t, we have got the equation. Okay, on the similar basis, when we make use of Maxwell's law for the ampere, right, we will get the electric field transverse component on the similar way. So directly you can write E of t, the way in which we got h of t in equation 8, we will get E of t is equal to 1 upon j omega epsilon, okay, into bracket del of t as it is. Only the thing is Ez is replaced with Hz, okay, plus deba by deba z of z cap. Et is now replaced with ht. Okay, equation number, let us say 9, where what is mu and epsilon, where mu is indicating permeability. Okay, and what is epsilon? Epsilon is a permittivity. Okay, so we need not to show the same derivation for making use of Maxwell's equation for ampere. We can directly write equation for E of t. Okay, so these two equations I will highlight. So equation number 9, we have got E of t, and in the previous equation, that is in equation number 8, we have got the equation for h of t. Okay, so what we do is, now we substitute h of t from equation 8 into equation 9. So what we do is, here in the place of ht in equation 9, we will substitute its value from equation 8. Okay, so let us substitute. We write here, substitute h of t from equation 8 into equation 9, So what we will get then? So we will get E of t is equal to 1 upon j omega epsilon into bracket del of t cross hz z cap, right, plus deba by deba z of z cap Okay, now here h of t, cross h of t we will replace from equation number 8, and which is given as minus 1 upon j omega mu, right, into bracket del of t cross ez z cap from equation 8, right, equation 8 is over, plus dabba by dabba z of z cap, right, multiplied by e of t bracket complete and bracket complete. Okay, so what we need to do now is you simplify this particular equation further and rearrange the terms. Okay, so what we do is we will simplify these equations further. We will solve on both sides, we will take the multiplication and we will simplify. Okay, so after simplification of this particular equation, what we get is e of t, okay, minus 1 upon omega square mu epsilon, okay, dabba by dabba z of z cap cross dabba by dabba z of z cross e of t, okay, rearranging the terms, right, is equal to 1 upon j omega epsilon del of t cross h z z cap, right, plus 1 upon omega square mu epsilon, right, dabba by dabba z of z cap multiplied by del of t into ez of z cap. You will get this particular equation when you simplify. Okay, so in this particular equation we multiply both side by omega square mu epsilon. So here I will write multiplying both sides by omega square mu epsilon. So you multiply on the both side of above equation by the term omega square mu epsilon. So what you get on the left hand side, when you multiply with omega square mu epsilon, I will get omega square mu epsilon e of t, right, minus I will get dabba by dabba z of z cap, right, cross dabba by dabba z of z cap into et cross, right, on the right hand side what I will get, directly I will write the equation, we will get direct omega mu by j, right, when you multiply on the right hand side by omega square mu epsilon del of t into h z z cap, plus when you multiply here again what you get, dabba by dabba z, right, cross del of t cross ez of z cap, right. So here what you can write, you can further simplify this equation, omega square mu epsilon e of t, right, minus dabba by dabba z of z cap cross dabba by dabba z of z cap cross e of t, you can write in this way, is equal to, now here if I multiply and divide on the right hand side by j term, so I can directly write as a j omega mu in this way, right, del of t h z z cap plus dabba by dabba z of z cap into del of t into ez z cap. Okay, now what we have done, we have substituted the value of h of t in e of t. Okay, and let us call this an equation number 10. Okay, now we will make use of vectoral triple product identity. Okay, so we know that in the vector mathematics, the triple product of the vector of vector, in vector algebra. How it is given? If there are three vectors A cross B cross C, so how this triple product of the vector is written as? This can be written as A into C B, right, minus A dot B into C. So this particular equation is a vector triple product. Okay, so this particular identity of vector triple product we will use in equation number 10. Okay, so in equation number 10 on the left hand side, okay, so on the left hand side of equation number 10 I will change the color, this one. Okay, so there are three vectors, dabba by dabba z, dabba by dabba z, and e of t. So let us make use of this vector identity over here. So dabba by dabba z of z cap cross, this is the first vector, second vector is again same, dabba by dabba z of z cap cross e of t. So this can be treated as A cross B cross C. Then kindly make use of the above identity. So what we can write then? Dabba by dabba z of dabba by dabba z of z cap dot E of t into z cap minus dabba by dabba z of z cap into dabba by dabba z of z cap into E of t. Right, now here we already know that the first term over here is going to be 0 because dabba by dabba z of z cap with z is going to be 0, and this can be written as this term, the first term is going to become 0, right? So this can be written as this, we when you take you will get dabba square by dabba z square E of t, right? So we know that why this is 0. This is 0 because two vectors in perpendicular plane, the dot product is 0. Okay, so that's why we can make it 0. Okay, so similarly on the right hand side over here in this particular equation, so what we do is we will apply this vector triple product in equation 10 on the right hand side. So here on the right hand side, when we apply the same rule, dabba by dabba z of z cap, this is the first vector, second vector is a del of t, right, and the third vector is ez z cap. Okay, consider this as three vectors A cross B cross C and apply this triple product identity. What we can write is del of t dabba by dabba z of z cap into, you apply this Ez into z cap, apply this property, minus into bracket dabba by dabba z of z cap into del of t, right, into Ez z cap. Okay, so here the first term over here, okay, so the first term is non-zero while the second term is a 0. This term will become 0, right? So what we can write, this is equal to what we get, del of t dabba by dabba z of Ez. Okay, so when we substitute these vector triple products in equation number 10, we can rewrite the equation number 10 now. So equation number 10 can be rewritten by substituting these triple product identities, omega square mu epsilon et, right, plus what we get over here, this particular term over here. Okay, so this is nothing but this one. Okay, so this minus and minus will become plus, right? So dabba square by dabba z square of et, and on the right hand side minus j omega mu into bracket del of t into hz z cap as it is, and this particular term, okay, can be replaced with this one. Okay, so what can I write, del of t dabba by dabba z of Ez. Let us call this an equation number 1. Okay, so here we know that the wave, total wave, is propagating along the z direction, right? So here we consider that the wave is propagating along the z direction. So when we take the space derivative along the z direction, so when we take the space derivative along the z direction, space derivative is indicated by dabba by dabba. Okay, so along the z direction it is dabba by dabba z. So this derivative we call it as a minus gamma, propagation constant, right? So call this an equation number 12. Okay, so when we take the double derivative of the space, dabba square by dabba z square. Okay, so what it will give? It will give gamma square. Okay, so call this an equation number 13. Okay, so by equation 12 and equation 13 we can write the equation number 1 as omega square mu epsilon e of t. Now this dabba by dabba z square, dabba square by dabba z square, we will write as it is. Okay, so this can be written as plus, what is dabba square by dabba z square? We can write this as a gamma square e of t, right, is equal to minus j omega mu into bracket del of t cross hz z cap, right? Now here dabba t, sorry, del of dabba z is minus gamma, so I will substitute here. I can write this as a gamma del of t e of z. Okay, del of t e of z. Now let us call this an equation number 14. So what I had done, I have substituted equation number 12 and 13 in equation number 1 and I got equation number 14. Okay, so on the left hand side equate the term, take the common term from the first two terms. E of t is a common, so what I will do is into bracket omega square mu epsilon plus gamma square. I will take e of t as a common on the right hand side. Okay, and on the right hand side I will write as it is minus j omega mu del of t into hz z cap minus gamma del of t e of z. Okay, so let us say we define the term, let us say we define a term omega square mu epsilon plus gamma square. Let us call this term as a h square. Okay, call this an equation number 15. Okay, so what we can write then, e of t is equal to, so how we can write e of t then? So the e of t is then given as e of t is equal to minus j omega mu upon h square, because this term we are going to take on the right hand side, so into del of t cross hz z cap, right, minus gamma upon h square, right, del of t into e of z. Call this an equation number 16. Okay, and similarly we can write the expression for transverse field component. So the transverse field component equation we can write h of t similarly as j omega mu, sorry, epsilon upon h square del of t, we replace hz with ez, similarly z cap, minus gamma upon h square, right, del of t, we replace ez with hz. Now we carefully observe equation number 16 and equation number 17. What we observe from equation 16 and equation 17? Say if you carefully observe on the left hand side of equation 16 and 17, we have the transverse component of electric field and magnetic field. Okay, and on the right hand side of equation 16 and 17 we have only z component, if you see. Okay, so what these equations are indicating? These equations are telling us that we have successfully implemented the transverse field component on the left hand side in terms of longitudinal field component which are expressed on the right hand side. Okay, so here we go further a little bit. So gamma over here, so here gamma we call it as a propagation constant. Gamma we call it as a propagation constant. Now you can recall from the theory of a transmission line, okay, so how the propagation constant is expressed. The propagation constant is expressed into two terms, real term and imaginary term, alpha plus j beta. Okay, so what is alpha? Alpha is called as a attenuation constant. Alpha is called as a attenuation constant. And what is beta? Beta is called as a phase constant, that we know. Okay, so if we take gamma square, then gamma square is equal to, on the right hand side, alpha plus j beta square. Okay, so how this can be written then? So this can be written as alpha square plus 2j alpha beta minus beta square, right? If you expand the bracket, right? So for lossless medium, okay, so for lossless medium, so what we can assume for a lossless medium, the attenuation is 0. For lossless medium, alpha is 0, right? So therefore the gamma square will become, when alpha is equal to 0, gamma square will become minus of beta square, please remember. Okay, therefore h square, okay, so the equation number 15, see from the equation number 15, what is equation number 15? Omega square mu epsilon plus gamma square is equal to h square, this particular equation. Okay, so here we can replace gamma with minus beta square. Okay, so what we get, h square is equal to omega square mu epsilon minus beta square. Okay, let us call this an equation number 18, sorry. Okay, now next procedure is to find expression for curl operation in 16 and 17. Okay, so what we have done in equation 16 and 17, we successfully implemented the transverse field component which are expressed in longitudinal field component. Okay, so next procedure is to find out the expression for the curl operation. Now if you notice equation number 16 and 17, the curl operations are indicated over here. Okay, we need to evaluate this. So we will evaluate the curl expression in equation 16 and 17, and then we substitute back the curl expression into 16 and 17, and then we simplify. Okay, so curl expressions can be generally given as, okay, so how the curl operation in mathematics, del of t, if there are two vectors, del of t and another vector, let us say psi of z cap, where psi is either representing electric field or magnetic field. Okay, so how this is expressed in mathematics? Okay, so it is represented as x cap, y cap, z cap, right? Dabba by dabba x, dabba by dabba y, dabba by dabba z, right? So only z component is there, so x component is 0, y component is 0, and the z component is a psi. Okay, this we know. Then if you simplify this, what you get? Dabba by dabba y of psi x cap, right, minus dabba by dabba x of psi y cap. Okay, let us call this an equation number 19, where the psi term, it could be either Ez representing Ez, electric field along the z direction, or it could be representing the magnetic field along the z direction. Okay, so as we know, here I write, as we know, gamma is given as alpha plus j beta, right? For lossless medium, we already know. For lossless medium, what we can assume? For lossless medium, alpha is 0. Therefore, gamma is equal to j beta, right? So we replace gamma is equal to j beta in equation 16. Okay, so equation 16, gamma we will replace with j beta. Okay, so what we get then? So we get, here I will write, replace gamma is equal to j beta in equation 16. Equation 16 is above over here. So in equation 16, what we do is we will replace this gamma term, okay, with j beta, right? So what the expression will become then? The expression is then given by E of t is equal to minus j omega mu upon h square, right, into bracket del of t cross h z z cap as it is. The gamma is replaced with the j beta minus j beta by h square, right, into del of t ez. Now let us call this an equation number 20. Okay, and how we take the dot product of two vectors? We took the cross product of two vectors with this matrix notation. Okay, so the dot product, the cross product of two vectors is shown over here with this matrix operation, right? So similarly we can take the dot product also with the two vectors. So how that can be represented as, so del of t into ez, sorry, del of t into psi, because we are representing that generalized term as a psi. Okay, so how this can be written then? So this can be written as daba by daba x psi of x, right, plus daba of daba y psi of y cap, right? Let us call this number 21. Okay, so here we can write del of t into, now you psi you replace with hz z cap, hz z cap. How this curl is written then? See here, we want to write equation for del of t into hz z cap. So how this can be written? By using the above theory, this can be written as matrix of x cap, y cap, z cap, daba by daba x, daba by daba y. There is no daba by daba z, it is a 0, right? There is a x term is 0, y term is 0, only ez component, and that is along hz. Okay, so when you substitute, what value we will get? Here I will get daba by daba y hz of x cap. If you simplify, take the matrix multiplication hz y cap. Let us call this an equation number 22. Okay, and similarly, how we can write the dot product h of t into ez? Similarly, this can be written as daba by daba x of ez x cap, right, plus daba by daba z daba y of ez y cap. Let us call this an equation number 23. Okay, so what we do is we substitute equation 22 and equation 23 into equation 20. Okay, so what we do is now we substitute equation 22 and equation 23 into equation 20, so you substitute these terms. So del of t into h z z, we, this particular term we take from equation 22, and del of t multiplied by ez, we take this term from equation number 23. So what we can write then? So we can write, when we substitute, E of t is then given by minus j omega mu upon h square, right? Here this term. Now del of t, this particular term I will highlight here, this particular term is replaced with this particular term in equation number 22. Okay, so I will write over here, this can be written as a daba by daba y of hz x cap, right, minus daba by daba x of hz y cap, bracket complete. Okay, next term is minus j beta upon h square. Okay, now the next term, what is that term? Here I will highlight dabba t multiplied by ez. I will take from this particular equation 23. Okay, so you replace that term. So what I get? Dabba by dabba x of ez x cap plus dabba by dabba y of ez y cap. Let us call this equation number 24. Okay, but what we know? We know that E of t. What is E of t? It is electric field along the transverse direction. So what is the transverse direction? Transverse direction to axis x and y. Okay, so this can be written as a Ex plus Ey. Okay, let us call this an equation number 25. Okay, so what we do is we equate equation 24 and 25 and separate in terms of x and y. So what we do is equation number 24 and 25 are same. We will equate equation number 24 and 25 and separate the equation in terms of x and in terms of y. So when you do that particular thing, so what you will get? The equation, see the equation for Ex and equation for Ey separately you will get. So here I will do that. So when you equate equation number 24 and 25 together, I will get Ex separated as, and it is given by minus j omega mu upon h square, right? Dabba hz by dabba y minus j beta upon h square, right? Dabba ez by dabba x. Let us call this an equation number 26. Okay, and similarly Ey component, when you separate that in terms of a y component, equating y component on the both side, so what you will get? Finally Ey, you will get the equation is equal to j omega mu upon h square. You will get dabba hz by dabba x minus j beta upon h square, right? Dabba ez by dabba y. Let us call this an equation number 27. Okay, so what we get? We got equation 26, which is representing electric field component along the x, and equation number 27, which is representing electric field component along the y. X and y, these are transverse field component, and if you observe carefully equation number 26 and 27, on their right hand side we have only z component, right, over here. So what we have completed? We have successfully completed in developing an equation of field components which are expressed in terms of transverse component on the left hand side, that is in terms of x and y, which are written in terms of a longitudinal field component. So the objective we have completed. So similar way, the magnetic field component can be also written as the expressions h of x. On the similar line, you can write directly. You can just replace j omega mu with the epsilon. Rest of the thing is same, h square. Hz is replaced by Ez minus jb upon h square, right? Now Ez is replaced with hz. Let us call this an equation number 28. And similarly, the magnetic field component along the y direction is given as h of y. How it is written then? Minus j omega. You replace mu with the epsilon. Rest of the thing is same. Replace hz with Ez, derivative of x, right? Minus j beta by h square, same. You replace Ez with hz. delta hz by delta y. Equation number 29. So what we observe from equation 26, 27, 28 and 29. Okay, so what we have written, Ex, Ey, Hx and Hy, these field components are expressed in terms of function of Ez and Hz on the right hand side, if you observe carefully. So we have successfully developed the transverse field component. So we, as already know, these are transverse field component, right? These are represented in the form of longitudinal field component, right? So here we have found out 4 equations for transverse field component, right? So the 4 equation for the transverse field components are given by Ex, Ey, Hx and Hy. All these are 4 transverse components, right? So there are 2 more equations, those are remaining. So these 2 equations are longitudinal field components, that is Ez and Hz. Okay, so the equation for Ez and Hz, 2 longitudinal component, are developed specifically to a particular waveguide. So as on when we come across a particular type of a waveguide, we will write the equation for Ez and Hz. Once you know the value of Ez and Hz, you can evaluate all the remaining 4 components, that is Ex, Ey, Hx and Hy. Okay, so the equation for the longitudinal field component will be specific for a particular given waveguide. So as on when we come across the rectangular waveguide and circular waveguide, we will develop the equation for Ez and Hz in general way. And once you know Ez and Hz, you can put these values into this generalized equation of Ex, Ey and Hx, Hy, which is given by equation 26 to 29. And then you can find all the field component of the given particular waveguide. Okay, so in general there are total 6 different field components are available, out of which 4 components are along the transverse direction and the 2 components are along the longitudinal direction or along the direction of propagation, right? So the generalized equation for transverse field components we have derived right now. Okay, and the equations for longitudinal field component, that is Ez and Hz, will be seen specifically to a particular given waveguide when we come across that particular waveguide, right? So this completes the derivation of deriving field equation of transverse field component in terms of longitudinal field component. Okay, now here this is the general way of finding the derivation and equation development for the field components. Now please remember that in the examination, this particular question will be hardly asked to derive the field equation components in a general way. Okay, but I took this particular derivation in order to give you the full understanding of how these equations are derived. Now please make sure that you are not supposed to derive this particular derivation in the examination. Okay, but you should know these 4 different equations which I will highlight over here. Okay, so you should know the generalized equation of transverse field component. Okay, so equation 26, equation 27, equation 28 and equation 29 you should remember anyhow. Okay, so you need not to derive all this derivation in order to come across these 4 equations. Okay, but please remember these 4 equations are in general representing the transverse field component, and these component equations we need when we analyze rectangular and circular waveguide. Okay, so for that purpose you need not to derive these equations again, only with some particular technique you need to remember these formulas. That is, you should recall and you should remember equation 26, 27, 28 and 29 and use it whenever a specific type of waveguide analysis is required. Okay, So what I will do is within the next 10 or 15 minutes I will show you a brief technique, okay, or you can say a trick in order to remember these particular four general equation in a short way. Okay, so what I will do is I will now tell you the trick to remember these equations 26, 27, 28 and 29. Okay, so see how I will start with. So you need not to by heart these equations, because you can remember that these equations are very difficult to by heart. Okay, so there is a easy technique in order to recall and remember these four equations, so that I will be telling you right now. Okay, so again I will repeat, this derivation is not at all required from your side to perform in the examination, but anyway you need to remember these four equations 26, 27, 28 and 29, because those equations are needed again, because these are representing general equation. So these are required as on when we come across analyzing a particular type of a waveguide. Okay, so what I will do is in the next 10 or 15 minutes I will tell you how to remember these equations. Okay, so I will write over here important step how to remember these equations. So I will write here steps to remember above field equation. You need not to by heart, because you need to understand it in a proper sequence. Okay, so what is the first step? So first of all, step number 1, if you want you can tape down these steps along with me. Step number 1 is write the correct polarities. Write the correct polarities on the right hand side. So what is this particular step? So first of all, you need to write equation for Ex, Ey, Hx and Hy. Okay, always you need to start with this particular sequence. So what is how you need to start writing the equation? First of all, you need to start writing as a Ex component. After Ex we have Ey component, right? After Ey you need to start with the Hx component, magnetic field component, and then Y component of a magnetic field. Okay, so what is the polarities of the term? So if you see equation 26 to 29, all these equations are consisting of two terms on the right hand side, first term, second term. Similarly here, first term and second term. Equation 28, first term, second term. Equation 29, first term and second term. So you need to write correct polarity for these two terms on the right hand side of all these four equations. Okay, so here we recall that it is a minus, minus, plus, minus, plus, minus, minus, minus. Okay, so you need to remember first term is minus, second term is minus. Okay, then for the second component it is plus, and second component is a minus. For the third component it is again repeated, first is positive and second is a negative. And for the last component Hy, it repeats as it along with the Ex, so it is a minus minus. Okay, so first step is to know the polarity of these two terms on the right hand side of these field equations, right? So Ex, Ey, Hx and Hy, minus minus, plus minus, plus minus, minus minus, you need to write first. Okay, so we go ahead and see what is the second step then. Second step, step number 2, how to remember. In second step we write multiplier terms. We write multiplier terms of both elements, multiplier terms of both elements on right hand side, on right hand side. Okay, what do you mean by multiplier term? So the multiplier term I will highlight. So what are those multiplier term in equation number 26 to 29? Multiplier terms are these: j omega mu j beta by h square. Similarly, j omega mu j beta by h square. So these terms you need to write for the two given terms on the right hand side. Okay, so the first term for electric field you need to write j omega mu upon h square. Second term is fixed, that is common for all, that is j beta by h square. And whenever the magnetic field comes, the first term you need to remember, you need to replace mu with a epsilon. Okay, so how we will write? So again I will write the equation Ex equal to Ey equal to Hx equal to Hy is equal to. So first of all I will repeat the first step of writing the polarity. Polarity is positive, negative, it is negative, right? Is negative and negative. Okay, and then positive, negative, positive, negative, and negative. So what is the second step then? Second step is write the multiplier terms on the both terms on the right hand side for each component. Okay, so here I will write, what is that second step? Multiplier term, that is j omega mu upon h square for electric field, and j omega epsilon upon h square. So here the term is j omega mu upon h square. That is the first multiplier term. So that's why it is multiplicative. Okay. Second term is common, that is j beta by h square. Okay. So if you see all the terms, j beta by h square over here from equation 26 to 29, j beta by h square. So you can write first, because the second term is common for all the components, j beta by h square, j beta by h square, j beta by h square, and j beta divided by h square, multiplier term. Alright. So electric field you need to write first term as a j omega mu upon h square, right? Now for the magnetic field you need to only replace mu with a epsilon, j omega epsilon upon h square. Rest of the things same, j omega epsilon upon h square. So second step is over. Okay, now in the third step. Okay, so step number 3. So what is the step number 3? In step number 3 we write remaining partial derivative terms. Remaining partial derivative terms on the right hand side. Right? So what is the partial derivative term? You again observe equation number 26 to 29. Partial derivative terms are these one, right, which I am highlighting right now. Okay, so you need to write these terms. So to write these terms, okay, so you need to first repeat and rewrite the first two steps. Okay, so what is the first two step? I will rewrite Ex, Ey, right, Hx and Hy. You need to recall in this organization. Okay, so what is the first term? First step, write the polarity, because I am going to repeat this above step again, minus minus, plus minus, plus minus, and minus minus. Okay, and next step was, the second step was writing the multiplier terms. I will first of all write the multiplier term for all the right hand side second part in this way, right? This is the second multiplier, which is a common for all the terms on the right hand side, right? And here j omega mu upon h square, j omega mu upon h square, and here j omega epsilon upon h square, j omega epsilon upon h square. Okay, now how to remember to write the partial derivative terms? Now this is a little bit tricky step. Now you need to focus very carefully how to remember. Okay, see here, this is x over here. Then you need to go with a cycle x and y. Okay, so x, that means we need to take partial derivative with next term, that is y. If it is x, you need to take partial derivative with y. Okay, and then which term you need to write? It is electric field. Now you need to write here as a magnetic field and z component. Okay, now as you wrote over here the partial derivative with y, on the right hand side you need to write partial derivative with x, right? And the hz term you need to replace with ez term. Okay, so this term is over here will become ez, and this term here it goes and becomes x. Okay, so first of all, again you write down for the second term. Here you need to start with a y. After y, what is the partial derivative? The partial derivative is x. Okay, because it, remember, it is not a dabba by dabba z. The partial derivative will only exist with along x and y. Okay, so y is there. After y, the x will come. So I will take dabba by dabba x. Right? The hz component as it is, you need to take here. As it is a dabba by dabba x you took over here, it will become dabba by dabba y. And this hz will again become ez over here. Okay, so in this way you need to remember. So similarly here we need to start with the x. X means you need to take partial derivative with next, that is y, dabba by dabba y. Okay, so here it is h. Okay, so here you need to replace with the electric field along z, right? So similarly here what you can write, you took dabba by dabba y. Now here it will become dabba by dabba x, right? And this ez will come over here and it will become hz, right? So similarly over here it is a y term, that means you need to take partial derivative with x, ez as it is, and this will become dabba by dabba y and it will become hz. Okay, so this is how, if you see that in step number 3 we have written the same field equations which we already received in equation number 26, 27, 28 and 29. Okay, so please recall this particular step in order to remember these equations 26 to 29. Instead of writing and deriving the whole derivation, this is a shortcut step in order to recall and conveniently write the transverse field component in terms of longitudinal field component. So I request you people to make a practice of these shortcut steps in order to remember the whole derivation for the transverse field component. Okay, so what we do in our next lecture, we will actually start with rectangular waveguide analysis. Okay, so in the rectangular waveguide analysis, again we will be revisiting and we need these generalized equations of field analysis. Okay, so whatever equations we saw today, that is equation number 26 to 29, and we also saw how to remember these equations in a simple 3-step procedure instead of remembering whole derivation. Okay, please remember these all equations we do need in the analysis of further part, that is in the analysis of rectangular waveguide and circular waveguide. Okay, so I hope you understood the whole derivative part and you understood the objective why we have done so far, and very importantly, at least you should know how to remember these equation in a shortcut way which I right now presented you. Okay, so again I will repeat, the whole derivation is not at all required from your side, but anyway you should recall and you should be able to write equation for all these 4 transverse components. Okay, and a shortcut method towards the last part I have shown you. So I request you people to go with the second method and to remember these equation with the second method which I have shown you. Okay, so in the next lecture we will directly start with analysis of rectangular waveguide, okay, and finding a specific component. So thank you very much for listening. and I request you people to have a practice of writing twice and thrice these steps so that you can easily recall these four equations. So thank you very much, and we stop here.